Hello, these are the solutions to activity 1 from recitation. How many quarts does 0.85 kilograms of ethanol occupy? We're given the density of ethanol, that's a property of the substance, it's an intensive property of ethanol. We're given 4 quarts is precisely 1 gallon, that's exact, and 1 gallon is 3.785 liters. Maybe not a super big detail, but that's actually rounded. If we wanted to look it up more precisely, we could, but this is certainly enough placeholders for our problem for this conversion here. In terms of what conversion factors, looking at these conversion factors, you may be wondering, do we have to memorize them? The answer is no. Don't worry about conversion factor memorization other than knowing how to do like the kilogram to gram conversion that we talked about. And then there's a few others that'll come up that are pretty obvious, like one maybe at this moment in time that I'm making this video that I haven't talked about in class, but we soon will, is that 1 cubic centimeter is exactly 1 milliliter. That's another common one that we'll just have to kind of know, but that's pretty obvious. Okay, and so you don't have to have these conversions memorized, but we should be able to solve for the number of quarts this way here. And so I'm just taking how many quarts. So I just want to start with what I'm trying to find. I'm going to begin my dimensional analysis step with what I'm given. And then I know that there's a ratio of 0.789 grams per milliliter, so I should probably go ahead and convert this to grams. So 1 kilogram is 1,000 grams. Oops, I don't need an equal sign yet. And then from there, let's use our density. I'm just going to use this like a conversion factor. So I can write that there's 0.789 grams per milliliter. So if I have 875 grams of ethanol, then I can use the grams per volume conversion factor with the density to calculate the volume of that sample. Now, I could have equivalently just said, okay, let's use D is equal to M over V, and I can solve for the volume and do some, cross multiplication and have volume equal to the, mass divided by the density, and I could work it out that way too. But we'll find, or very often in this class, we're going to use dimensional analysis a lot, and this problem is really meant to show us how to put dimensional analysis into use. I have a milliliter, right now I have my unit in milliliters, but we need to get the quarts, and the quart conversion is from gallons and from liters. So let's go milliliters to liters. So I know there's 1,000 milliliters in 1 liter. And then from my conversion factor here, for every 3.785 liters, that's 1 gallon. So I've gone from milliliters now to liters, and from liters to gallons, and then finally from gallons, 1 gallon is 4 quarts. 4 quarts in a gallon. Now, if you're not from the US, maybe you've never seen the quart unit before, but this is just, a problem that takes us through conversions where we're putting dimensional analysis into practice. So I've canceled gallons and I've ended in that unit that I'm looking for of quarts. So if we do this math here, 0.875 times 1,000, divide by 0.789. I'm going to hit enter just to see that that would be about 1,109 milliliters. So I divide that by 1,000 to go to liters. That's about 1.1 or so liters. And then I divide that result by 3.785 to go to gallons. So that's a little less than a third of a gallon multiplied by 4. It's a little bit more than a quart. So it's 1.17 quarts. Now, in terms of, again, where I'm at the moment I'm making this video, probably not the moment you're going to be at when you watch the video, is I haven't yet talked about sig figs to the class. But by the time you see this video, you will have probably seen and heard about significant figures. What's really important with significant figures is that we recognize that when we have a measured quantity, which is what this is meaning to show us here, we have this measurement or presumably measured quantity of 0.875 kilograms of ethanol, that quantity there has 3 significant figures. And then This value here is probably also based on a measurement, so this is also subject to our sig fig rules. That's 3 significant figures. And then if I look at these other quantities, these are exact. Like this is, well, technically rounded, but at least 4 sig figs. I can look up more if I need to. A conversion factor is rarely going to lead me to round my results. When I'm looking at my steps here, I don't, for example, with the 1,000 grams to one, per 1 kilogram, I'm not rounding that to 1 sig fig, right? That's exact. So I still have 3 sig figs. I then divide by 3 sig figs. So 3 sig figs divide by 3 sig figs. So I still have 3 sig figs. This is exact. This is at least 4 sig figs. I can look at it more precisely. Rarely should a conversion factor lead me to round at any point. And then this is an exact definition. There's exactly 4 quarts in a gallon by definition. So I'm keeping all 3 digits here as being significant. So sometimes we get confused with sig figs on when do they apply, when do they not apply. There's a couple questions that get at this, but they involve the quantities in our work and our problems that are the ordinary lab measured quantities, not the exact values, not things that we know are either counted or defined or precisely known, like 1 kilogram is exactly 1,000 grams. That's not going to lead us to round to 1 sig fig. Okay, so what is the difference between the following numbers? This is getting at kind of what sig figs are getting at here. So we see 1.05 times 10 to the 3 meters, 1.050 times 10 to the 3 meters, 1,050.0 meters, and 1,050.00 meters. So these are all actually representing a number that looks like 1.05. I'm just going to rewrite this here to show that that would be 1,050 expressed out to meters. So this would be 1,050 with 3 sig figs, with 4 sig figs, with 5 sig figs, with 6 sig figs. So these are all representing the same value, but with greater precision. So this would be the least precise number, and then this value here is going to be the most precise. And then if I were to write, say, this number here, that this number here would be 1, 2, 3, 4, 5 digits are significant. This one, and so this would match 1, 2, 3, 4, 5 sig figs here. So these numbers here are exactly the same number. So 1.0500 times 10 to the 3 is the exact same representation of the number 1,050.0 meters. Both of those are that value precisely given to 5 significant figures. Our least sig figs was 3. This is that value to 4 sig figs. We already said that's the 5, and the final one to 6. So this is just the least precise to the most precise giving of that number 1,050. Question 3 here, which corresponds to an exact quantity containing 3 sig figs. And so just moving a few things out of my way here. Okay, so I have 125 students that I counted precisely. So no funny business here. This would be, we go through with a precise, say counter, where we are exactly and precisely counting in a room that there's exactly 125 students in that room. Nobody's left, nobody's entered. We haven't miscounted. We've double, triple, quadruple checked. We are certain those 125 students. This is an exact quantity. Anytime you can count precisely and exactly, then it's exact. If you are approximating there to be 125 students, if you're in the, say, business of approximating crowd size, that's an estimate. That's a prediction. That's something that's going to be subject to how precise we can give or know that value. For example, if you have a large crowd, you could say to yourself, well, how precise are you ever going to estimate that crowd? You might be able to get it to the nearest 1,000 or 10,000 or 100,000, depending on the circumstances and the technology you have at your ability. But you're probably not going to be able, with a large crowd, to very exactly count every single person in attendance. Now, they kind of do this at baseball games, where they kind of count people coming in like a turnstile, say at a football game, but those are also subject to people not really rotating the turnstile through properly and all kinds of other funny business that can go on. So small people, we can count them, we know that's exact. This is not 3 sig figs. So I look at 125 counted students, that's not 3 sig figs, that's exact. That's like an infinite number of significant figures. Whereas a $100 bill, this is also exact. Money is like really exact. You know, like if I said you need to buy three things that cost $1.25 each, you know, and you're at the store, you know, buying this, and so you're doing this arithmetic here, and you're saying, okay, you know, that's going to be, what's that going to be, $4.75? Am I not, am I able to, no, I'm sorry, $3. I was doing silly math quickly in my head and screwing it up. That's going to be $3.75 if we're talking money. So we're talking money, you buy three things, it's $1.25 each, assuming there's no tax on this item, you owe the cashier precisely $3.75. You're not going to say, hey, can you round that to one sig fig, please? And that does not apply. That's a different type of problem than if we said, well, do the same problem, but, you know, like imagine you measured one side of a some sort of object's 1.25 meters, and then you use a different tool, and the other dimension was only 3 meters. And the thing that is really complicated here to think is, like, imagine you have some sort of object here, and this object here, let's say this dimension, I went at it with a really precise scale where I could determine very precisely that this was 1.25 meters. I'm not showing the scale, but I'm just imagine you use a very precise ruler that lets you determine that object to the nearest, you know, hundredth of a meter. And then let's say this other ruler, we use a terrible ruler where it had a 0 marking, had a 5 marking, didn't have any graduated markings on the side. So I'm looking at this saying, I don't know, is that definitely looks more than 2, doesn't look to be quite 4, so let's call this 3. And so the uncertainty here is really big. You know, when I see a measured quantity that's 3, that's much different than a counted value that's exactly 3. Exactly 3, we leave this result at 3.75. In fact, we'd say that that's exactly how much you owe to an infinite number of significant figures. But if we are talking about the volume of this object, it would be like the surface area, the area of this object, we'd round that to 4 square meters if we're talking the idea of this being 3 times 1.25, where it's 3 times 1.25 meters. Now the key is if I use the same device that I determined 1.25, I could probably determine that to be 3.00, or more precisely whatever the length happens to be for that dimension. Then I could report that area to, you know, 3 sig figs. But if I'm using this crappy tool, I only get 3, I'm rounding that to just 1 sig fig. Getting a little bit off topic here, just looking at this question, coming back to it. So a $100 bill exactly, you know, has an infinite number of significant figures. That's an exact quantity, not subject to sig fig rules. It's not 1 sig fig, it's not 2, it's not 3, it's not 4. It's an exact quantity. So now I see a balance. So I'm looking at a balance, and it says 1.00 grams for some object on the balance. This is where our sig fig rules are applied. So that is 3 significant figures. And I think that's a really hard thing, and that's why I'm trying to stress it here in this video, is that, you know, determining what sig fig rules apply to, they apply to ordinary lab measurements or things that we assume when we look at numbers that have some sort of ordinary length unit, that's some ordinary lab measurement now, not a perfectly known number or exact quantity. So looking at question 4, I see 2 addition problems, 294 plus 295. Which result should be reported to 4 significant figures? So let's take a closer look. So I have 294 plus 795. I'm adding these up. Now, there's 2 ways we can look at addition. One is if we just use the rule. So the rule of significant figures for addition and subtraction say, when I'm adding and subtracting, I'm going to line these up by their decimal place, and I'm going to round to the value that's of greater quantity. And so I'm looking at 1's placeholder plus 1's placeholder. Without doing anything, this result is good and precise to the 1's placeholder. And so that would be 9, that's going to be a 4, and that's going to be 1049, and I'm adding meters here, and so that's going to 1049 meters, and so all 4 of those digits should be significant. Okay, so 4 significant figures for this quantity here, so that's good. And I'm going to come back to in a second why that works out, but let me look at the next quantity just real quick. Just applying the simple rule of 795 added to this. Again, I'm looking at the placeholders here, and I get 0. I put a 1 here to do the arithmetic, and so that gives me 5, and then that gives me 1050. Of course, we could throw this into a calculator, and I'm just going to Whenever I shorthand arithmetic and do it in a video, I easily make mistakes sometimes. So that's really 1050, didn't make a mistake. Meters. Now the question is, and this is where, a lot of times we can get confused by sig fig rules. If I said in a different context, I just said you look at a balance and the balance says 1,050 meters, I would probably say, or if I just wrote that down in a different context, I would say that looks like 3 sig figs to me. But now this problem here is a different context. I've taken two values that I know are good to the ones placeholder, so I know the result, just like 1049 is good to the ones placeholder, 1050 is good to the ones placeholder. If I wanted to report this result and be unambiguous here, I'd go 1.050 times 10 to the 3 meters. If that's fundamentally a different number than 1.05 times 10 to the 3 or 1.0500 times 10 to the 3, those are all the same basic number, but with a different precision associated with it. So this properly shows the result to 4 significant figures. So the second result also has 4 significant figures. So the answer to this question should be that both of these addition steps should be reported to and have 4 significant figures. Now let's come back to a why question, why this works. So and what's really going on here? Now, the idea of taking any kind of measurement is that, if you imagine we have this object, my pencil keeps turning off and is annoying me, but okay, so imagine we're measuring this with some sort of a device, and then what we would probably have is, if we're reporting it only to the nearest 1 meter, we probably have some sort of a measurement that's being made where we might have something like 250 versus 260, and we're trying to interpolate where that actual measurement is falling. And we're going to have some disagreement if it should be 254, if it's 255, or it's 256. And so there's going to be some plus minus here, some uncertainty in the last digit in the number. And if there was an uncertainty, if we were exact that it was 254, if we knew that it was exactly 254, then we would have said, well, then maybe it should have been reported to 254.0, and we would have known another digit. So imagine a different context. So imagine we have the same object that we're measuring, and I'm just trying to draw a different object. Now I'm just going to measure it with a different type of ruler or a different type of measuring stick. Now imagine this one here has graduated markings between it. So I have, maybe 254 here, and I have 255 here. And so maybe this device here, every centimeter, or I guess it'd be every meter, has a marking. And then I can determine between here that maybe it looks like 254.3. And so if I had a better device, I could more precisely determine that length. And the issue here is not what is the actual length of any object that we're considering. The question is, how well was it measured, or how well are we assuming it was measured by the number we see in a problem? So 254, I'm assuming there's at least 1 unit of uncertainty in that value. 795, again, the minimum uncertainty is plus or minus 1. It could be greater. This just means that the last digit in the number has some inherent uncertainty associated with it. And so imagine what this means for a result. If it was 254 plus or minus 1 plus 795 plus or minus 1, in statistics, you're probably not going to be surprised to learn that the result here is about 1049 plus or minus about 2. And this plus minus, if you knew this really well, let me change colors, if you knew these two uncertainties really well, and you knew how to do the statistical analysis, which if you take a stats class, you might learn how to do this, you can more precisely calculate this quantity here. And so you can kind of see the uncertainties falling in that ones placeholder. And so that's why when we add and subtract, we really look hard at the placeholders. Now, if we do another analogy of, what if we had 25.4 plus 795 meters? Now, the implication would be that we probably just use 2 different types of rulers to make these measurements, but I'm going to round this value here still to the ones placeholder. So I now have tenths placeholder plus ones placeholder. This result here is going to be rounded to the nearest 1 value. So this result here would be rounded to 830 meters with 3 sig figs. So addition, subtraction are all about where the placeholders line up. Multiplication, division are all about counting significant figures. That'll be on the next question. So this question here, I have 35 times 35. how many sig figs should I report that result to? Well, let's just write this out. Don't necessarily have to do this, but if you write it out, you probably, if you throw it into a calculator, you see 1225. It's a volume, so this is square meters as the unit that we'd report the result to. Now, how many of these digits are significant? And so for this result here, I had 2 sig figs times 2 sig figs. The result is only good to 2 significant figures. So we actually would need to report this result to 1200 square meters. So now the issue is not that if you had a perfect 35 by 35 volume that you should round it. That's not what this problem is getting at. This problem is saying if you've measured, like, let's say, one dimension of a room, but very imprecisely that it's only 35 plus or minus 1 meter, so the implication is your uncertainty here is plus or minus 1, your plus or minus 1 here as well for the second value. Imagine you do 34 times 34. Let's throw that into a calculator real quick. 34 times 34 is 1156. And let's go up to 36 times 36. That's up to 1300, 1296 to be precise. And you can see that the plus minus is falling in the hundreds placeholder. And so we're seeing that plus minus fall within the hundreds placeholder. And so if we learn how to propagate our uncertainties here, we're going to see that the plus minus is probably over 50 square meters, meaning our plus minus is falling in the hundreds placeholder here. So the really simple rule when we're multiplying and dividing is we just count sig figs. 2 times 2 sig figs, we always round that to 2 sig figs when we're dealing with inherently measured quantities. Okay, so this 35 meters inherently was measured. It looks like a measured quantity or a quantity we could measure. This is representing an ordinary lab measurement as well, so we report this value to 1200 square meters. If I wanted to be able to round to 1225, I would have to have a better way of measuring the volume to be 35.00 times 35.00. Now, think of it this way. We're not trying to say, or even factor in, what is this object that we're assuming or imagining? What is its real volume? We're trying to say, based on the measurements we've taken of it, what is the best we can say with some uncertainty is its, in this case, area. I keep saying volume, but this is really an area, and we're just doing length times length or length times width. So how well can we know or report or be confident in the calculation of this area? The answer is not vary with 2 sig figs times 2 sig figs. So if I wanted to be precise enough to report the result for this area to be 1225, I need to go find a better tool to measure the actual length and width of the object. Then if it comes out to be 35.00 times 35.00, then I know it's 1225. But maybe if we more precisely measure the dimensions of this hypothetical object, maybe we would find it's not precisely 35.0. Maybe it's 35.15 by 35.25, and then we get a different number altogether. Okay, so let's take a look at this question 6 here. So this is just a sig fig problem where we just have to sequentially apply the sig fig rule when we add, we have to apply the sig fig rule when we subtract, and then we have to apply how many sig figs. I see I forgot to unbold this. I need to do that in a minute. But then we need to think about the multiplication rule when we multiply. So when I have multi-steps, our sig fig rule is that we need to apply the addition subtraction rule when we add or subtract. We need to apply the multiplication division rule when we multiply or divide. So it's just an order of operations. We apply the proper sig fig rule. So let me do 12.45 plus 7.234 meters. And so adding and subtracting is all about our placeholders. And so let me throw that into a calculator. 12.45 plus 7.234. If I just write down the calculator, it says, what I get on the calculator screen, 19.684. And so then that's going to be good to the fourth significant figure. So it turns out that number there is good to 4 significant figures. I don't necessarily have to round it. I don't want this to be overly confusing because, when you take an exam, if you round this versus don't round it, I think you'll be just fine. I don't think you're ever going to get a question wrong. But Generally speaking, we tend to round at the very end, but we note that that result would have four significant figures. So in my head, I'm kind of saying, okay, that's good to the four significant figure. I can carry out the next step and look at its sig figs and taking the difference here. And so now when I take the difference, I don't just look at 4 sig figs minus 4 sig figs and round it to 4. That would be the multiplication division rule. I have to look at my placeholders again. I have to round it to the placeholder quantity that's greater. That's the hundredth placeholder. And so my calculator says 5.126. So I'm going to round that. Or if I wanted to round it, we go to 5.13. And so this value here only has 3 sig figs. So if I take 3 sig figs times 4 sig figs, the multiplication step should be rounded to 3 significant figures. Now let me actually do and finish the problem. So you can either do 19.684 times 5.126, just knowing that that's 3 and 4 sig figs respectively each. And then when I get that result, I get 102.67. And I just know I'm rounding that to 3 sig figs. So I call that 103. And then looks like meters times meters, so that's square meters is our unit. So if I wanted the actual numerical answer, it'd be 103 square meters. Now, if you come back to the step here and say, well, what if we had just rounded that to 19.68? What if we had just rounded, I wrote this wrong, sorry about this, but this was really 216. I used the right number in my calculator, I just wrote it down wrong. I wrote it down incorrectly here too. I don't know if I said it right, but I just wrote it wrong. But in any event, if I had rounded this to 5.22, and we do the step of 19.68 times 5.22 where we rounded, I bet we still get 103. And we do, we still get 103 square meters, still 3 sig figs. So you can round, it's okay if you round like in a textbook problem, on an exam problem. Where premature rounding becomes an issue is like on a lab report where you're doing like 6 sequential steps. Generally just round off once at the end so we don't introduce added rounding errors. This gets too off topic, maybe not, I don't know. But there's a little bit more significance in the 4 than any other number. So when I say 19.684, even though eventually if I was reporting the result of that to 19.68, that would be the correct way to report the result. There's a little bit more significance in 19.684 versus 19.68. So there's a little bit of significance in this number here, so we can carry it on to the next step if we wish. More important for lab than for lecture problems. Okay, so for this one here, I'm converting 1.25 micrometers to centimeters with no conversion factors that I should look up. And so the key here is trying just to use what micro means, what centi means, what we know about those, and try to use our memory of that. And so I'm going to use the mental analysis, number of centimeters, or what I'm looking for. And so that's what I'm starting with. And then that's what I'm looking for. I start the problem numerically with what I'm given. I can then think, well, how does a micrometer relate to a meter? 1 meter will be a lot of the little micrometer. So it's 10 to the 6 micrometers in 1 meter. And then 1 meter is 100 centimeters. So a lot of the little centimeters in the meter. So 125 divided by 10 to the 6. And then times 100, I get 0.0125 centimeters. Number 8, I'm told that iodide and Ki are both ionic compounds with much higher boiling points in water. Ki is soluble in water, but PbI2 is insoluble in water. Which separation method is best? I think we're told that their boiling points are high, so we know that distillation is probably not going to be a good idea. We tend to do that for like liquids. So distillation is probably not a good technique. Chromatography, like if we think of adding these things onto some sort of solid material. I don't know. That doesn't sound to me to be a good separation technique. What makes sense here is because we're told they have a difference of solubility in water, why don't we just add water to the solid? So you have a solid mixture, so add some water. And then one of the compounds will dissolve, the Ki will dissolve into the water. So I then should be able to filter the solid that remains. That remaining solid will be the lead iodide. And then we can then separate the solid from the solution that has the water and the Ki. Then I should be able just to evaporate that water, and I lose the water, and I'm left with just Ki. So I now separated my solid Ki from my solid lead iodide. We actually do something like this in one of the lab experiments. This kind of links up with something that we'll do. So the best thing we can do here is just add water. We can't filter the solids because they're both solids and they're kind of mixed equally together. That would just be some sort of homogeneous mixture. So an analytical balance appears to not be correctly calibrated because every time we take the mass of an object, it's 1.2542 grams too high. Now maybe we figure this out because we go find, those like little test grams that you might have used or think of using for like a balance, like you maybe use in high school where you're actually adding physical weights to one side of a balance to weigh an object. Well, maybe you have some of those precise massed objects that you can add to an analytical balance to check its accuracy, and you find, hey, it keeps recording a measurement that's too high every single time. And so would we say that the balance is accurate, precise, one of them, neither? So accuracy is how close we are to the target, and every time we're missing the target. So it's like, if we're shooting at playing darts, we're aiming at the bullseye, but we're hitting off to the side every time. So we're trying to aim for the bullseye on our target, but we keep missing. But every time we keep missing in the same spot, and so that's clearly not accurate. We're missing our target, so we're not accurate. But we are actually being pretty precise. So we are still precisely hitting the same target, even though it's not. We're precisely hitting something. It's just not the intended target. So hitting the target is accuracy. Repeatability is precision. So we're being repeatable, but not precise. The density of an object, what is the density in grams per milliliter of an object with a volume of 1.95 cubic inches and a mass of 1.25 pounds? Try to use only these conversion factors here. We would always give these ones to you if you need them. So an inch is 2.54 centimeters, and a kilogram rounded into pounds is 2.2046. Again, we can look it up more precisely, but that should be good enough for this problem here. And so to me, this looks like something I hopefully can think about dimensional analysis with, but let me think of one thing before I get started with my dimensional analysis. I see cubic inches here and I see inch here. And so if I think of a cube, and I'm obviously not the most skilled artist, but I'm imagining a very terribly drawn cube, but just picture 1 inch by 1 inch by 1 inch. In terms of a perfect cube, that would be 1 cubic inch, right? So 1 by 1 by 1 cube object in terms of inches would be a cubic inch. And so then if I then say, well, that's 2.54 centimeters, that's 2.54 centimeters, and that's 2.54 centimeters. If you remember, if you haven't seen this, that's exactly the number of centimeters in an inch, like exact by definition. So centimeter to inch is a exact definition, so not 3 sig figs, exactly 3 sig figs. And so if I then think, okay, now my object in cubic centimeters is going to be equal to 2.54 cubed centimeters cubed. So 2.54 by 2.54 by 2.54 is 1 by 1 by 1 inch. And so now, I don't know if I want to work this out. I guess I will because I'm already putting it in my calculator. This is a kind of a weird step here, is that this result is really 16.387064 cubic centimeters precisely. So this is the exact number of cubic centimeters in a cubic inch, because we started with exactly 2.54 centimeters. I cubed it, and I don't think my calculator rounded this. I think it would have showed me more digits, and so I think I've seen this number before too. So this is precisely how many cubic centimeters, like exactly how many cubic centimeters there are defined to be in a cubic inch. Okay, so whenever I'm doing a cubic conversion, like if I'm doing a cubic meter and I want to convert that to cubic centimeters, and I'm trying to do that conversion, I just think 1 by 1 by 1 meter would be 100 by 100 by 100 cubic centimeters. So it'd be 100 cube centimeters cubed. So I have to cube my conversion between the length unit that I'm converting with my cubic unit. So 1 inch to centimeters, 1 inch is equal to 2.54 centimeters. 1 cubic inch to centimeters cubed, I cube that conversion factor. I cube the 2.54. So one cubic inch is 2.54 cubed centimeters cubed. Now, the way I tend to think about this is hopefully I understand this conversion. So then when I get to a problem like this, I'll just try to use dimensional analysis. So I'm going for grams per milliliter. And so we got 1.25 pounds per 1.95 cubic inch. And hopefully I can do the conversions for the pound into grams, or perhaps into kilograms and grams. So I go 2.2046 pounds per kilogram, and 1 kilogram, 1,000 grams. And then my inch conversion here, again, I think my conversion from inch to cubic centimeters, so 1 inch cubed is going to be 2.5. Well, let me take this back a step. So the way I tend to think of the conversion is if I know that for every 1 inch, that's 2.54 centimeters, but I know that I have the cubic inch, then I know I have to cube my entire conversion factor. So I have to cube the 2.54 to get cubic centimeters. And so that's how I can know that I'm cubing my conversion factor. And then we just have to know, and a very common conversion is that a cubic centimeter is precisely and exactly 1 milliliter. And so this problem here will look like 1.25 divide by 2.2046 times 1,000. I'm going to hit enter. That gives me 566.996 grams. And then I'm going to divide that. I'm going to do the calculation for the numerator separate. So I got 1.95 cubic inches times 2.54 cubed, 2.54 caret 3. And that's 31.95 cubic centimeters, and which is a milliliter. I'm just trying to write down enough placeholders. So I got 3 sig figs. I haven't changed off of that in the numerator, and then the denominator, I have 3 sig figs, and this doesn't cause me to round. Nothing caused me to round. So I got 3 and 3. So I should end with 3 sig figs. It's really not a sig fig question, but why not think sig figs? So I go 566.996 divide by 31.95, and I get 17.7 grams per milliliter. Answer D. Okay, tricky problem perhaps, but one where we can understand and try to comprehend. A problem like this is really trying to make sure we understand that cubic conversion between cubic inches and centimeters, cubic centimeters. Okay, so let's take a look here. We got nitrogen with the black sphere in this diagram, hydrogen with the white sphere. And so it looks like I have 4 of those particles that are just randomly distributed in a container. It looks like it's depicting some sort of a gas substance, and the substance would be a compound. I have 2 elements present. It's a molecular compound. Looks like NH3. That's a molecular compound. And then uniform throughout would be, does this appear to be homogeneous? It appears to be equally mixed, so it appears to be homogeneous to my eyes. And then the non-variable composition is, do I see any other molecules there? Do I see just NH3? And I do. I don't see any other molecules. Like if I saw something that looked like this, where I saw, okay, in my diagram, it showed something else like this, I'd be like, okay, that's a non-variable composition. That means I have a mixture. I would have some sort of a mixture if I saw this, but not seeing that, given that my picture doesn't have this, then I have myself a non-variable composition. So all the above would apply here. So non-variable composition just means all the substances are the same compound or molecule being represented. So I have the same NH3. So this molecule, it's a compound, uniform throughout, homogeneous substance.